Let's start. Hello, let's start our today's DSA Journey with this amazing DSA visualizer by dsa.chicode.com. Use this link to get a 7-day free trial. So this is our today's question: Kth smallest in a sorted matrix. Given an n cross n matrix whose rows and columns are each sorted in ascending order, find the kth smallest element in the matrix. Consider its sorted order, counting duplicate values separately. Okay. So if we actually go to this question, it will be much more better that given we are given an n cross n matrix where each of the rows and column is sorted in ascending order. Okay, so it simply means this one. If I take this example, like yeah, this one. If this is our matrix, okay, this is our matrix. You may like, and yeah, if we just put it here, this is how our matrix will look like. So see 1, 5, 10, 1, 5, 9. This is sorted. Also 1, 10, 12. This 3 is also sorted. So 5, 11, 13. See 10, 11, 13. 9, 13, 15. Okay. It is the actually the matrix is sorted in row wise order. So every row is sorted, every column is sorted. Okay, but not necessarily the matrix is sorted, just like the 13 here, but the next element will be 12. Okay, but it satisfies these two conditions, like it is sorted row wise, it is sorted column wise. Okay, so we have to find the kth element, like what we are given to us, like kth smallest element in the matrix. Okay, kth smallest element. So our approach could be like this. Okay, so I just take it from the question already. It is very easy, the brute force approach. We are taking the matrix and the k. We just flat this. If we flat this, it will become 1, 5, 9, 10, 11, 13, 12, 13, 15. Okay, now we just have to sort this. Okay, so if we sort this, I just make it sorted. It will be 12, it will be 13. Now it is sorted. Now goes to k minus 1. And what is our k? Given to us or not? I think it is 8. For this question, this is 8. So just if our matrix is this array will become A, so it will become k minus 1. This will be our answer, like k minus 1. So 8 minus 1, 7. So 0, 1, 2, 3, 4, 5, 6, 7. So this 7 is 13 and our answer is also 13. So this is our simple. We just take the matrix, we put every element into a vector or an array, we sort that, and we just return the k minus 1 index. So if we just go and just simply add the solution here, and if we just return it or evaluate it, it should work. It's working. Okay, now we will be doing the optimize and the binary search approach. Okay, so this is a searching problem, and if you remember, some previously we do some searching problem also, where we calculate the mid, and then we simply goes like to the section, like how many section we have, like go to the lowest part or the highest part. But here they will mention that the matrix is sorted in like in row order, in column order, but the whole matrix is not sorted because see here are 13 and then 12. Okay, so it is not sorted, but every row is sorted. See, every row is sorted. Also every column is sorted. See, every column is sorted. Every column is sorted. So what we can do is basically this will be our the lowest element and this will become the highest element. It will always become true because I tell you why. The array is sorted. Okay, this simple list 159 is sorted. Okay, so this one should always become the less. Okay, then if you go to column wise, okay, the one is the first one, that's mean it is always the smaller one. And why this is the biggest one? Because if we go to this one, this 9 is greater than 1 and this 15 is greater than 9, and column wise it is sorted in ascending order, so 9, 13, 15. Okay, so there is a high chance that this will be our high. Simple. Our low will become, suppose M is our matrix, it is simply 0 and 0, and our high will become simply matrix of M minus 1, N minus 1. Okay, now calculate mid. Simple. 1 plus 15, 16, 16 by 2, 8. Okay, can. Okay, now we have to go to the vector, go to the matrix and search for the element, count of the elements whose value is greater than 8, oh sorry, less than 8 or equal to 8. So we have to find elements whose value is less than or equal to 8. So how many? 2. 2. We have to get the count 2, 1 and 5 because all of them are greater than 8. We have to found the count of the smaller or equal element to mid. Okay, count the smaller or equal elements of mid. Simple. So if this count somehow greater than our k, then simply this will become our answer maybe, and we have to go to the smaller part, otherwise go to the bigger part, or h will become mid minus 1, and else it will become al equal to mid plus 1. Simple binary search. So what we are actually doing, this, we are searching that if there are at least k element which is less than mid, then the kth smallest element can be the mid or something smaller. Simple. This is the simple approach we are using. The simple question we have to answer every time. We have to calculate the count every time and then simply check it is possible or not. Okay, so we don't need this. Okay, now I think I should write the pseudocode because it will be much more easier. So we are given a matrix and a key. Simply our L will be our matrix of 0, 0, and our R will become matrix of sorry n minus 1, m minus 1. And while L is less than equal to R, simply do one thing, our mid will become L plus R minus L by 2. And now we have to count, like count of smaller element, smaller or e equal, smaller or equal elements of mid in the matrix. So in the matrix we have to find the smaller or equal to element the mid. If any chance our count is become greater than equal to k, it simply means one thing: we already reached the answer, or the answer is the smallest one. Okay, so we just put our answer here, and our r will become mid minus 1, and otherwise l will become mid plus 1, and at the end just return answer. Yes, it's working perfectly. Wow, this one. This is our simple approach. Now I already written the code here. Should I explain this or rather write it? We just take the reference. We can take reference from here, and now just write it. So first we need to go and check the size. N will become the matrix of size. Okay, this will become number of rows, and our m will become column. So matrix of 0 dot size. While not while, our first we need to take the low and high. So our low will become matrix of 0 and 0, and our high, let's take it as high, become n minus 1 into m minus 1, which is the last element. So now calculate low is less than equal to high. Simple binary search technique. Calculate mid, which is nothing but low plus high minus low by 2. Then we need the count. We will do it by just calling a function, and it take the matrix and the mid. Okay, and if the count is less than equal to k, or sorry, if the count is greater than equal to k, not less than, then do simple thing: answer will become the mid, and our high, because we have to go to the smaller part, that if any smaller answer present or not, mid minus 1, and else low equal to mid plus 1, and we don't take the answer, so our answer will become starting with minus 1, and at the end just return the answer. Okay, not the return answer. Now we have to calculate this function, or write this function. So it will be simply this, but I will just change the thing. This will become the mid. Okay, so we have to find number of elements. Simple thing, we have to find this function, like in this function we have to find the number of, we have to see, we have to find the number of small number of elements smaller or equal than mid. Okay, we have to just find this. For this I first we have to calculate this. Okay, now how could we find this? So the most efficient way to finding this solution would become using a binary search. Why? I just view with this. Yeah. So see, everything is sorted, every row is sorted. Okay, so if we go to every row, if we just go to every row, if we just go to every row and apply binary search on this, if we apply binary search on this 159, we can easily find the number of element actually greater smaller than or equal to 8. Okay, so how could we find that? We will take a count starting with 0 and we will return this count. Okay, now we have to do one thing. We just need a for loop because we want to go to every row and then apply binary search. So we just go to 0 till n for every element. We have to, rather than applying binary search, we can actually use one thing, and that the thing is called upper bound. Okay, so first I have to write it. What does it takes? It takes simply one thing, our matrix dot. Okay, so it will take the whole vector matrix of I dot end with the middle value, and at the end just do matrix of I dot begin. Let me just, so this will become our count. Simple. Now I think it should work if I just run it, or rather I will check. Yes, it is working. And if we submit it, it should work. Yes, it's working perfectly. And now everything should be fine. Everything should be fine. Rather than this thing, this upper bound. Okay, let me just bring back things. This one. Okay, so we are using this formula. Simply, if you see this, this is row begin, row end, the middle value, row begin. Here we don't take any row, we just take matrix of I, and matrix of I actually given us the whole row. Okay, the whole row given us as a vector. Okay, and we just check if the number of value is less than mid. Here we are checking. So why we are doing this? We want to find how many elements in the entire matrix value less than or equal to this mid. Okay, so we want to find this thing, how many values are present in the matrix, so that's a less than or equal to mid. Okay, because every row is sorted, we can independently find how many element in each row less than equal to mid. Upper bound give us an iterator pointer to the first element that's strictly greater than mid. Okay, what this line want to say? See, 1, 5, 9, and suppose our mid value is 8. So what this upper bound function, this upper bound points, go to 1, checks it is less than mid, yes. Go to 5 and checks it is less than mid, it will be checking using this value. Okay, and this is just the whole row, like we just give you the whole row, go and check into the whole row with this mid, and when it goes to 9 it will stop. Suppose this is point I. Okay, this is 0 1 2, this is at point I. Okay, now why we do this matrix of I dot begin? Because we want the count. So how many numbers here are less than 8? 2. How will do this? What will be the matrix begin? 0. What is the I? 2. 2 minus 0. It will simply become our 2. So number of element less than 8 in this array is 2. In this vector, in this array, whatever you want to. For that, this upper bound will go and check into the array like how many are less than the mid, and then its point to the point where either our array is ended completely, or we just reach this kind of a point where our value is greater than, and then simply do it will return the index, and then we return it with the begin to get our number of values. Simple. Why it is working? Because it is sorted. So if it will be like 10, like, or 11, 12, 8, then it will always stop in the 9, and we can easily use it because the array is sorted. So whenever it is stopped, the further values or the more right values which present into the right portion is also greater than the mid. Okay, so this is the first point. That's why we are using this matrix dot begin and the upper bound. Okay, see, upper bound find the first number greater than the value. You can consider this value as mid. It is its position tell us how many number are less than equal to value. What is the value? For us, the value is mid. Okay, remember this thing. Okay, so at the end, just we do this thing, number of element of row I that are less than equal to value. Okay, this is the simple thing we do. And actually what we are doing into the matrix, we just binary search on the value, and for every value of mid we just count how many element less than mid, and if the value somehow is become greater than or equal to k, we got our answer. This can be possibly our answer, and we go to the more lower part to get any lower value, that if any possible lower value present or not. We just do this, and then if this is our not greater than equal to k, we just go and increase our low. Simple. So this is the question, the whole question. I think I explain everything. Also this is I will take this. So this is the time and space complexity. This is the time and space complexity in log range. Okay, so range is our array range, and n is the value of the array. Actually, value of the matrix, we are given n into n matrix. We also take m here, but if we don't take m, it will not bother, because if we just take n here also, it should work, because it is an n cross n matrix. Yeah, it should work. You may take it, you may not take it, it doesn't matter, because we are given an n cross n matrix. So this will become our time complexity, and this will become our space complexity. Okay, so this is how we solve this question, k smallest element in a sorted matrix. Go check this platform, use this link to get a 7-day free trial. Link is in the description also. Thank you very much. Go check out this platform at dsa.chaicode.com. Thank you very much.